All right, everyone, welcome to my latest virtual weather and climate office hour. Today's will be a hybrid session in the sense that I will talk a little bit about events that have recently occurred in California, including, in particular, the record-breaking rain event stemming from the persistent atmospheric river north of San Francisco last week and the flooding that did and did not result from that. And then I'll talk about another atmospheric river that is starting to make landfall as we speak. It won't bring nearly as significant of impacts or nearly as intense of rainfall, and it will hit a different part of the state, but it's still notable weather worth talking about. And then I'll touch a little bit on the long-term outlook or at least the medium-term outlook for California as we head into December, which actually looks, speaking of hydroclimate whiplash, very different once again, with a strong indication of a persistent period of much drier, if not completely dry conditions, and warmer weather almost everywhere in the west, except in places, if you're in interior valleys where you get trapped under the fog and cold, which might be especially true in parts of the Central Valley at time. This is now classic Tule fog condition. And the time of year is pretty classic for that as well. So I'll get into all of that and more in just a moment. But as always, just want to remind folks that this channel is sponsored by Reask, a climate tech company that is rethinking extreme weather risk in a warming climate. So, and thanks to those of you who managed to catch this session. I changed the timing at the last minute because tomorrow's originally scheduled timing at the last minute will not work for me unless you want to hear lots of banging on pipes in the background. So I decided I would shift that up to today and actually do an evening session because I know that many of you are more available later in the day. And I am going to try and do more sessions later, where and when possible, to reach folks who aren't available to join live during the core daytime, could call it 9 to 5 working hour period. So the first thing I want to talk about is the rain event we had last week in California. Some of you are saying, what rain event, if you're in Los Angeles, which many of you are in Southern California. Some of you in San Francisco Bay Area are maybe saying, yeah, it rained, but big deal. Maybe you're in the Santa Cruz Mountains or something where we've seen many far larger events in recent years. But if you're up in Sonoma County, in Santa Rosa, or in Mendocino County, you're probably not wondering what rain event, because the rain event you just experienced was the heaviest rain event of your life. And I can guarantee that unless there are some people who are significantly older than 100 years old, and in some locations perhaps multiple hundreds of years old. So I'm really getting up there in the unlikelihood, unless I'm very wrong about the nature of human longevity. Anyway, the reason I say that is because the rain that occurred in places like Santa Rosa and in nearby environments on 2 to 3 day timescale, so over a 48 to 72 hour window, was the heaviest such rainfall ever observed, including at the long-term climate recording site in Santa Rosa proper, which has a record going back to, I believe, around 1906, which at this point is getting close to 120 years ago. So there's been no rain event with this precedent since then. And if you use statistical analyses to extrapolate a little bit farther and say, okay, so if it exceeds all of the recorded rain events in this region on 2 and 3 day timescales, just how extreme was it in a broader context? And of course the answer is we don't know for sure, because if we only have 120 years of data, then strictly speaking, we can really only estimate that it was probably more than a 100-year recurrence interval event, at least in the climate that prevailed for most of the past 100 years, which is arguably different than the climate we now have today. But if you use those statistical techniques, as has been done with tools like the NOAA Precipitation Atlas, which I've referenced on social media threads on this topic regarding this event, the 48 to 72 hour rain accumulations were broadly a 100 to 500 year recurrence interval event for a good portion of 3 counties in northwestern California, starting with Sonoma and going north from there along the coast. And at least in one location was considered to be a 1,000-year recurrence interval. So essentially you would only see a rain event that intense in a stationary 20th century climate once in a given millennium. So that's a big number, and I am nearly 100% certain it's wrong. So I'll be a little bit bold there. I am virtually certain that certainly in today's climate, that was nowhere near a 1,000-year rain event. Arguably, it's not even that close to a 100-year rain event anymore, even though it was, in fact, the largest event in over 100 years for sure in some of these areas. So I'm going to break that down a little bit into a couple of different pieces. First of all, let's ignore climate change for a moment. And I say that as a climate scientist who's very worried about climate change, and we'll bring it back into the conversation in about 2 minutes. But let's ignore it just for a moment for the sake of argument. Ultimately, we have, in most places, about 100 years of rainfall data. And even if we assume that the climate hadn't changed at all over that period, even though we know that it has, 100 years of data is frankly not very much from which to determine the rarity of very rare events. Now, imagine we're only talking about an event with, say, a 25-year recurrence interval. So one that on average, a magnitude of that event occurs every 25 years or so, about 4 times per century. This does not mean, by the way, that there's any particular recurring cycle. So a 100-year event does not mean it occurs on a 100-year cycle. A 25-year event does not occur on a 25-year cycle, nor does a 1,000-year event occur on a recurring 1,000-year cycle. There is no inherent periodicity or cyclicity to these sorts of events. And so when we talk about, say, the N-year event, let's just call it the 100-year event to make it less awkward to say out loud, what we're not saying is that this event happens every 100 years exactly or even approximately. It just means that there's approximately a 1% chance that that event happens in any given year. So if the number of years it takes on average to have an approximately 100% chance of seeing that event, you multiply by 100 and you get the number of... Now, even there, it's not the case that you absolutely have to see an event after 100 years. You could go 3 centuries without seeing a 100-year event. At least assuming you've defined it using a broader context. So if you use 1,000 years of data, say we had 1,000 years of rain gauge data, which we don't anywhere on Earth, even in the very longest rainfall records generally don't go back more than 2 centuries, and even that's unusual. That's mostly in just a handful of locations in places like Western Europe, where we have high-quality rainfall data going back that far. Let's assume we had 1,000 years of daily rainfall data. If we did, then we might be able to confidently estimate what the actual magnitude of the 100-year event is. Because if I had 1,000 years of data, I would say, okay, what is the maximum value that occurs 10 times? So what is the essentially what is the 10th most extreme value from all of those 1,000 years worth of data? And then we might say, okay, that's probably pretty close to the 100-year event, because we know that not just randomly taking any given century from there to say, okay, what's the wettest event in any given century? Do we really think that's representative of what the wettest event of all of those 10 centuries in a given millennium could have been? Probably not. You're going to get a different number for each randomly selected century, even if the climate isn't changing, just due to random chance. As you imagine, the weather doesn't occur on an exactly repeating pattern over and over again, and so you can get different random sequences of weather, some of which will be more extreme than others. So if you wanted to estimate the actual magnitude of a 100-year rainfall event in a given place, ideally, you'd have 1,000 years of data. Even better if you had 10,000 years of data, or a million years of data to work with. But of course we don't, and in most cases we're limited to about 100 years of data, or less in some cases. So then we use statistical techniques to sort of gap fill. But the problem is, inherently, if you only have 100 years of data and you're trying to estimate the 200 or the 500 or the 1,000-year event, you're extrapolating well beyond your observed set of information. And the problem is, you can probably extrapolate a little bit. So, if we have 120, 130 years of data, it probably isn't too ridiculous to estimate the 150 or maybe even the 200-year recurrence interval event, because we do have the 90-year event that we observed and the 75-year event that we observed that can kind of fill out the upper portion of the curve in terms of probability. But if we're talking about the 500-year event or the 1,000-year event, we really don't have any information about what the statistical distribution looks like that far in the tail, and so we're kind of wildly extrapolating with statistics. And sometimes we need a number, right? We need to work with something, but there's very high uncertainty into what that actually looks like when we're that far out in the tail. Do I think our 100-year recurrence interval estimates are close to being correct? Yes, with one big caveat. Yes, assuming that the climate hasn't changed. I think we have about enough information to estimate that. 200 years, maybe. In some situations, it's close enough. 500-year events, 1,000-year events, I don't think we have a good handle on what those events look like, and I think we may be systematically underestimating their magnitudes. That's my semi-empirically supported hypothesis, is that this is not a statement about climate change yet. It's just a statement about the methods we use, the sparsity of the data available, and in some ways, our lack of imagination and integration of thinking about processes rather than just looking at the raw statistics. So one way to deal with that potentially is to run large ensembles of weather and climate models to generate thousands of years of synthetic data. So you can run the 20th century-like climate 100 times. Well, now you have 1,000 model years of synthetic data of climate that's equivalent roughly to what could have happened in the 20th century. And so from that, you might be able to get a better estimate of what the 100-year event would be, because now you only have 100 years of real-world data, but you could run it through a model, get different randomly generated sequences of weather that are consistent with that kind of climate, and now you have a synthetic sample of 1,000 model years. So you've increased your sample size, you have a higher N, great. Why don't we do that all the time? Well, now the problem is it's not real-world data. It is still a model. All models are wrong. Some are useful. That's a statement that will probably never not be true. But the point being that there are trade-offs either way. You use a process-based model, you can increase your synthetic sample size, but you're never 100% sure that it's correct, because ultimately it isn't the real world, it's a simulation of the real world. If you use just the raw observations and extrapolate well beyond your observed distribution, well, then you're sticking with data that's is correct, but you don't actually know if what assumptions you're making about that statistical distribution well into the tail is reasonable. And that's assuming that there's no change in climate. Now let me get to the other point about climate change. We know the climate is changing. We know conditions are warmer than they used to be. We know that in many regions of the world that extreme precipitation events and extreme temperature events and extreme whatever events we're talking about have already increased. And that can essentially make the upper tail, so the most extreme part of the statistical distribution for any given weather quantity, very sensitive to even small shifts in the average condition, because the events that are way out there in the tail of the statistical distribution, bit of a tongue twister there, are already so exceptional that it doesn't take much of a nudge to put you into completely different territory. So the difference in magnitude in many cases between the 100-year event and the 200-year event is considerably smaller than the difference in the magnitude between, say, the 5-year event and the 10-year event. So this is getting into math and statistics, and I don't want to get too into the weeds here. Some of you may have followed all of that. Some of you may have only followed pieces of it. But the simpler version of it is this. I think that we systematically underestimate the likelihood of very extreme rainfall events or very extreme storm, very extreme heat wave events, whatever the case may be, even ignoring climate change for a moment just because of the methods we use to make those determinations. I also think we are further underestimating the likelihood of these events because the climate is in fact changing and pushing us in the direction, generally in the world, of more extreme heat, more extreme precipitation, more extreme drought, more extreme wildfire, whatever the case is, events. And that compounds the issue. So we both have a pre-existing underestimation from using historical methods, potentially in many cases, and we also have a further underestimation given that the methods, even if they were perfect mathematically and statistically, generally don't account for the non-stationary climate, the warming climate that we know is real up to present and is going to be even more real moving forward. So what does it mean that parts of Mendocino and Sonoma and adjacent counties saw somewhere between, I think it's fair to call it somewhere between a 50 and 1,000-year rainfall event? Wide range there, but I'll just be very conservative with those uncertainty bounds. It means that it was quite an extreme rainfall event by any objective measure, and yet probably not as extreme as is depicted using these statistics because we underestimated the background likelihood and because climate change is going to be making these events significantly more likely for the rest of our lives. So what's some good news in all of this? Well, the good news is that the events we just saw, this very persistent 3-day atmospheric river, which was not necessarily record-breaking in its short-term intensity or instantaneous intensity, but was record-breaking for its combination of intensity and duration. It just sat over the coast at strong but not extreme intensity for days on end and brought this record-breaking rainfall. But what we're lucky is that this was the first major rain event of the sequence and arguably even of the season in some places. Rivers were not running high before this event. Reservoirs were not dangerously close to overtopping before this event. Soils, in fact, were still relatively on the dry side. So the soil column first had the ability to absorb those first few inches of rain. The rivers had a lot of room to rise, and in the North Bay they did rise to flood stage and above in many cases, but they did not raise to major or extreme flood stages. They were in sort of the nominal minor to maybe moderate locally flood stage. What's remarkable is that these rivers rose from near summer-like lows all the way to minor to moderate flooding over the course of just 3 days. So just imagine if this storm sequence had occurred when those rivers were already near bankful or in minor flood stage. What would have been the magnitude of the flooding that resulted from this storm then? Clearly, it would have been dramatically worse and would have been a much greater disaster. As it was, there was widespread flooding, and I'm sure some people experienced losses and damage, but it was not a catastrophe. It was not an extreme flood disaster, and it very well could have been had the antecedent conditions been wetter, had the rivers been running higher, had this not been essentially the first big event of the season, but had it come later, closer to the seasonal peak of runoff and rainfall, and been either preceded and or followed by stronger storms. This is essentially the scenario. This is the arc storm scenario, where you get an event like this, but it's embedded within an even longer sequence of similarly intense events that prime the soil and then follow up with the 1, 2, 3, 4 punch. We didn't get that. This was sort of the one big one, although it was very big. We're lucky that it didn't come under different antecedent conditions. We can't guarantee that we will be so lucky the next time, and I suspect there will be the next time. But in this case, it was mostly creek flooding. I think the damage was real but modest in scope for the most part, and it did have the side benefit of pretty definitively ending fire season, I think, from the Bay Area northward. So that's the other piece of good news there. And actually, I want to show something briefly on screen while I'm talking about this. So you're going to see my infinite mirror briefly before I pull something up. This is just a graphical indication of the places that actually saw a 100-year rain event on a 72-hour period. So of course, this is a map. This is a tool by Russ Schumacher, Colorado State University. He pointed this out to me, and it's a pretty cool tool. You can see the URL, since I think you can see my whole screen here. But anyway, it gives you, in real time and a recent archive of extreme precipitation events and how they compare to the estimated recurrence intervals. And subject to all the caveats I was just talking about recurrence intervals, it's still a very useful tool to determine whether a recent rain event was truly extreme or not. And as you can see, the units here, of course, are millimeters, as are most scientific units in metric rather than inches. But, this is 1/4 of a meter. So the yellow region is places that saw more than 1/4 of a meter of rainfall, which is a huge amount of water. And it's a huge volume of Northern California that saw that. But as you can see, the relative rarity of the event was greater in some places than others. So there's a broader region that saw this extreme amount of water. The areas in red are the places where this was actually believed to be at least a 100-year event on a 3-day timescale. So this includes, again, Sonoma County, Napa County, Mendocino County, and then also a swath of counties across the northern Sacramento Valley into the northeastern foothills as well. This was a very intense rain event, and we are lucky, again, that in all of these places this did not occur under wetter antecedent conditions. If we look at a higher recurrence interval, so if we go to, those are places that exceeded 100-year. If we look at the 1,000-year recurrence interval, got to bring this up here, as you can see, there's only 1 or 2 points or 4 points, I guess. So 4 nearby points, essentially in Sonoma County. This is very close to Santa Rosa, where the event is believed, according to this metric, to have been about 1,000-year recurrence interval event, right, centered on Santa Rosa. Again, I have my doubts subject to this caveats, but it does indicate at least that the event was most anomalously, record-breakingly extreme right around Santa Rosa, although there was a broader area where it was something closer to a once-in-a-century event. And if I set a slightly shorter duration, a 48-hour duration, that was for the three-day accumulation window, there were no 1,000-year points there, but there are, I believe, there were even more for a 48-hour period, extending across a broader portion of Northern California, places that exceeded their 100-year recurrence interval for 48 hours, so for 2-day rainfall in this region as well. If I look at 24-hour, which is the last thing I wanted to look at this, were there any places that exceeded their record 24-hour total? Well, there were a couple, again, near Santa Rosa and then one other point on the northeastern point of the Sacramento Valley, but generally this event was less impressive for its 24-hour, and I bet you if I telescoped to 6-hour, I don't think anybody will have seen a record here. No, during this event, no location in California came close to a 100-year rain event for the 6-hour period, meaning that the intensity of the precipitation in the short term was not record-breaking, but the cumulative precipitation over 24 to 72-hour periods was progressively more extreme as you use the longer time aggregation windows. So that's all I really wanted to show with this one. I think I'm going to take questions as I go here, just given the context, and I'll move on to the next thing in a moment. By the way, I added a link to our documentary on climate extremes. Many of you may have already seen it, but if you haven't, I'd encourage you to check it out after the session. The link is in the comments section again today. Comments that it's still raining in Redding, or rain in the Santa Cruz Mountains as well. Definitely some ongoing rain in between, and it's been locally heavy. There's even been some thunderstorm downpours in the unstable air in between storms. Fortunately, nothing that's causing too big of problems. It's also not super widespread, but it's been locally heavier. Yeah, as Matthew points out, 7.5 inches of rain near Oroville, and over 6.5 inches upslope near, or I guess that's south of Oroville, Bangor. Yeah, south. That's quite a lot, and as I mentioned, you can kind of see those red points on the map, indicating, reflecting that, where these are places where that amount of rain was highly unusual or even record-breaking. Fortunately, again, this is essentially what I want. The first, just to wrap up that first segment, the fact that the antecedent conditions weren't wetter, that the rivers weren't running higher, that the soils weren't wetter, and that this was the first storm and really the only storm in the sequence for Northern California, was the reason why record-breaking rainfall did not translate to record-breaking flooding. Rain and floods are certainly related, but it's not a one-to-one correlation, and the background conditions really do matter. All my hydrology colleagues with whom I'm currently working on a number of projects in this space would certainly agree with that statement, despite sometimes those two things being conflated. Okay, so the next thing I want to do is talk about the next atmospheric river storm, and I'm going to share my screen once again. All right, so I'm going to zoom in a little bit again here. So this is sort of the broad view. This is the European model, and I'm just going to step through time. You can see that this is suggesting that the next round of rain is on our doorstep already. It's arriving in the Bay Area now-ish, and the Central Coast within an hour or two. And this rain will mainly be focused on a corridor from the Central Coast into the southern Sierra Nevada. As you can kind of just see, this atmospheric river is draped there and then kind of just peters out, not really making much southward progress. So you may notice that there's a pretty sharp edge to the rain once again as you get close to Ventura or Los Angeles counties. LA may see a little bit of light precipitation out of this, but frankly, probably not very much. And far southern California will remain mostly or completely dry. So certainly a have or a have not situation once again, just illustrating that this system, and it is an atmospheric river. I'll bring up the precipitable waters. You can kind of see this atmosphere. This is going back in time a little bit. And now this is the current situation right now. You can see this atmospheric river moving. Let me scroll down a bit so it's easier to see. Again, this is right now, atmospheric river moving across central and parts of Southern California from north of Ventura County primarily, but also south of the San Francisco Bay Area primarily, and into the Southern Sierra before sort of fading away. Total precipitation from this right now, the heaviest precipitation certainly looks like it's going to be in the Southern Sierra Nevada, where there could be some jackpot regions at the very highest elevations of 4 to 6 inches of liquid equivalent. At 10,000 feet elevation, at very high elevations in the mountains, this is going to be snow, so very heavy Sierra cement. Lower to mid elevations, this will essentially be rain, so there could be some localized but mostly minor flooding in the Southern Sierra Nevada, mainly because, again, antecedent conditions are very dry. There's a lot of room for the rivers to rise. There's a lot of soil absorptive capacity for those initial few inches. I'm not expecting really a significant flood event nor record-breaking rainfall, although it could get pretty heavy in the Southern Sierra and the Southern Sierra foothills. As you can see, along the central coast, even a good soaking from about Monterey southward to about San Luis Obispo, maybe a little bit, maybe if you're lucky, down as far south as Santa Barbara. But again, a pretty narrow section of coast. Showers continuing in Northern California, but nothing all that heavy by Northern California standards. So this really is going to be, as I'll bring my drawing tool out once again so you can see it, this really is going to be an event that's let me just get those lines to stay. Pretty much this is the corridor of significant precipitation from this event. Fortunately, it's not overlapping, as I mentioned, this region here that saw very heavy precipitation from the last event, so not really any significant flood concerns up there because the rain just won't be that heavy with this event, and not super significant flood concerns even here at the core of the atmospheric river because it is both weaker, faster moving than the last one, and is once again occurring in a place where the preceding conditions were pretty dry. As I mentioned, the exact southern cutoff for this event is unclear, but it will probably be somewhere like this, and that does mean that much of LA and San Diego, and maybe perhaps even the majority of California's population in this region may not see a great deal of, if any, precipitation from this event. So this actually means that despite the record-breaking rain event up here in the end of November, most of Southern California, at least in this area, will end up well below average precipitation for the autumn. So that would have been true for most of Northern California too, but then of course we got the extreme atmospheric river saved by the bell at the very end, kind of skewing those seasonal statistics, but certainly going from abnormally dry to abnormally wet, and now maybe going back toward abnormally dry in some of these places based on the outlook for the next few weeks. I'll show that in a moment. But generally, this is what this looks like this is sort of what it's looking like right now. If I bring up the satellite imagery, you can see this is what it looks like over the northeastern Pacific. Let me draw the atmospheric river on there. Here is your atmospheric river, essentially. It's a nice, pretty one once again, coming in from the southwest. There's some subtropical influence, so it'll be fairly warm. But what we don't have, there's a low pressure system here, but it ain't no bomb cyclone. Let me put it that way. So compared to the last one, this is just a much weaker low, and so it's driving a weaker atmospheric river despite the presence of moisture. So the winds won't be as strong, the rains won't be as strong, and it won't be as persistent. So that's why this one is of lesser significance than the last one, but still a decent early season system, bringing some much needed rain to this portion of the state. And you can see again, this is sunset. So that line that's sweeping, this is essentially the program deciding where there's not much to see with the visible satellite imagery because it's dark. So on the east of that, it's switching over to a different product, which is the infrared view over here, and I'll bring that. I'll just put on a different. This is one that is not sensitive to daylight because this is water vapor and that is always visible via the infrared sounders. Again, just showing a different picture of this. You can see some nice convection. There's some thunderstorms out there over the Pacific. I don't think those will make it inland, although I suppose there's a slight chance along the central coast that there could be a little bit of lightning associated with this, but that moves inland. But again, the AR essentially, well, actually, let me redraw that. That's not quite right. But the AR essentially looking like this. That's the main corridor of flow here. So north of that line, some rain, but nothing too big. South of that line, little or none, because this system, despite its low latitude positioning, is kind of going to come like this and then just kind of peter out before making it all the way. All right, and then the next thing I wanted to show is zooming out a little bit, what the broader scale pattern looks like. I'll go to the North Pacific. This is a view that's always nice to see. And if I go to the normalized, let me just go to, yeah, I'll do this. This is good. So this is the broader view, and I'll go to the European ensemble, since I always like to look at ensemble forecasts for larger spatial scales and longer time scales. Just making sure that you're seeing what I'm seeing here. So here's where we are now. This is that low pressure system right now, moving into California, bringing the atmospheric river. As I mentioned, it isn't actually going to make it all the way to California. It's just kind of stay out there southwest of California, kind of peter out as we move forward in time. Zooming in a little bit to make that a little bit clearer, actually. And then as we get toward this coming weekend, we see a pretty strong signal for significant ridging building in the Pacific Northwest, and then over California as well, and then really encompassing most of the West through potentially as long as mid-December. This is the European model, so let's look at what the American model ensemble says. And do we have similar ridging? We do. So we have a similar strong ridge developing. I'll bring that over to the actual height anomalies here. A little more pronounced here. And potentially persisting well into December. The other piece that's interesting, and I'll switch back to the European model here. This is a pattern that's kind of classic for a pattern that looks like it might produce some interesting weather in California, but doesn't really quite get there. So what we see is anomalously low geopotential heights in the Western Pacific and this really strong Pacific jet extension like this. But sometimes what this does is if the jet streak doesn't extend all the way east to California, in this case it doesn't, what it really ends up doing is pumping up this geopotential ridge. So what it really does is you have this accelerated flow here, but then you're depositing all of that excess momentum and energy and moist static energy into right about here. And what this ends up doing is you have accelerated winds here. You have a strong jet streak. You have very active storms. You have low pressure systems bombing out over here and doing all sorts of crazy things. But what this ends up doing is advecting warm and stable air northward here and sort of building this ridge along an axis near the west coast. And so this is really this is a storm blocking ridge if it pans out this way. And we see this we call this the North American dipole pattern. We've published some on this. It's also there's also known as the TNH pattern. There's various acronyms for teleconnection patterns that kind of resemble this, but the general idea is this, with a big ridge along the west coast and a big trough here and a trough over the Pacific with the jet extension here. This is potentially favorable for warm and dry conditions in this region here broadly, active Pacific storm track but to the west, and then potentially cold as you get Arctic air that dives southward and then eastward here on the eastern seaboard. This is a pattern we saw a lot during 2013, 2014, and remember some of the big drought years. This is not saying that we're headed for a big drought necessarily, since this is only a pattern for a couple of weeks following what was literally a record-breaking rain event in some places. But it is interesting to see this pattern emerge because we know it's favored when we have a warm West Pacific as we do in this region right now. So what we could tend to see is when there's anomalous warmth in this part of the Pacific and the tropics, what we do tend to see is exactly this, an enhancement of the Pacific storm track immediately north and downstream. So we have low pressure systems and a jet stream here. But then, as I mentioned, this sort of tends to like to build the ridge up here and sort of have an axis here. And this is one reason why it's not just a question of La Nina. So La Nina is more relevant near the eastern tropical Pacific Ocean. Again, this is the equator labeled down at the bottom here. La Nina means cool waters in the eastern equatorial Pacific. We're sort of maybe not going to see as big of a La Nina as we thought previously, so that may be less of a player this winter. But the really warm western tropics remain, and this can drive this sort of pattern independent of what happens with La Nina. La Nina can reinforce it, but sometimes this is all we need, and right now we are seeing that kind of pattern develop pretty classically, with a trough axis here, a ridge axis here, and then another trough here. So what does that mean in terms of sensible conditions in California? I'll zoom back into the western U.S. here. Again, right now, pretty strong indications of a honkin' big ridge in the west. But in practice, what does that mean? It means that the west coast becomes really anomalously dry again. So we actually could have a couple of week periods. You see that initially, like in the short term, this atmospheric river bringing wet conditions just to that narrow strip of central California, but the rest of the window, most of California and the rest of the west, unusually dry for early December. Again, in places like this follows record-breaking rainfall, so this is not a problem per se. It's a little more of an issue down in coastal Southern California since they have not gotten the rain yet and won't with this event. And the other thing that it's interesting is that this will probably be, if you're away from cold air trapped in valleys, it's going to be pretty warm. So as we go from a cooler than average conditions now to, if I scroll down a bit, you can see this better, all the reds and purples are warmer than average as we go towards early December. In fact, that's quite a strong signal for highly anomalous warmth, except for, and I thought this was really fascinating, even using coarse resolution ensemble modeling, you can see the Thule fog developing in the Central Valley. So in this region here, take a look at that. That's quite the signal for an inversion layer. Again, I'm going to draw on it so you can see, and then it's going to auto erase so it goes away. That's one heck of a Thule fog signal in the Central Valley, because what will then happen is that all of the locations above 500 to 700 feet in elevation will be much warmer than average during this period, potentially even balmy into the 60s and 70s, really unusually warm conditions. But all of that damp air from the rain we just got or are about to get in the San Joaquin Valley will likely be trapped under a stable inversion layer and create the potential for persistent, day-long, very dense fog. It can be cold and clammy in the Central Valley here, while it's warm and balmy and dry everywhere, but fog in the Central Valley. And what I think is fascinating is that, again, even at this coarse model resolution, you can see some of that cool air spilling out through the Carquinez Strait into the parts of the Bay Area. So this could be a case where you go to the Carquinez Bridge or something in the Solano County, Central Valley, cold and clammy under the fog layer, potentially for days on end. Watch out if you're driving on I-5 or I-90 or Highway 99. That could be a major Thule fog, pile up car auto crash scenario. We often see that happen during these dense Thule fog events. But if you go up, say, to Mount Hamilton or Mount Diablo or Mount Tam, it might be 70 degrees and sunny above that inversion layer quite potentially during this period. Also, notice just that this is a big ridge, that's a big, broad warm signal just about everywhere. So whatever snow we've started to accumulate we might not be adding a lot to it starting in a couple of days, and it might even start to melt at lower elevations due to this warmth, even at higher elevations. So quite an interesting temperature anomaly map. Generally broad warmth, but then you can see, and then even in this depiction, it even has some of that cool air spilling out toward the Farallon Islands from that cold, clammy air. So this may or may not be literally true, but I do think this is a pretty strong signal of a Thule fog pattern with potentially cold and clammy temperatures in the Central Valley under the fog, and then warm, mild, and balmy and dry just about everywhere else. Could see some similar behavior in some of the higher valleys in the Rockies. I think that's what's going on here with this blue blob in Utah surrounded by reds. But anyway, that's the broader pattern that I foresee heading into December, and why I think we might see that pattern recur again later this winter. It would be quite remarkable if we started off the winter dry after receiving literally the heaviest rain event on record in parts of Northern California. It will turn out to be somewhat fortuitous if that's the case, but fortuitous and striking, I suppose, not being mutually exclusive. All right, so I'm actually going to go back. You're going to see me you're going to see me stop screen sharing. You're going to see me again, and it's time for me to answer, I think, some questions. So let's just see what's coming in here. Mary asks, the whiplash is hard to get used to, but this very wet to very dry thing is part of climate change expectations. No? Yeah, that's correct. And that is something we expect to emerge in California. In fact, we just wrapped up a review on hydroclimate whiplash in a warming climate. This will be a Nature review paper coming out hopefully in January or February of next year, so now imminently. We've been working on this for over 3 years. It's actually been quite a long and involved process with colleagues within California, the US, and internationally. And this paper has a global focus, and I'll talk more about it once it's available in the wild, so to speak, once the paper itself can be viewed by everybody and it's gone through the copy editing and all that. But I'll talk about that in early 2025. But the short version is, yes, we do expect to see increasing hydroclimate volatility here in California, and indeed just about everywhere else on land in the world. And as most of humanity lives on land, this is going to be an emerging theme more broadly for just about everybody, although to different degrees, depending on where you are, and depending on the number of degrees of warming globally, quite literally, and also the flavor of that whiplash, whether it's a bigger increase in the wet versus a bigger increase in the dry. You can get an increase in that whiplash from either or both. You can get roughly the same number of wet events but more dry events, you get more whiplash. You can get more dry events but roughly the same number of wet events and have increased whiplash. And of course you can increase both of them and also see an even larger increase in whiplash. So there's still, regional dynamics at play, but overall and in general, that is something that we expect to be an emerging theme. So I'll have more to say about that in early 2025 with some, hopefully, graphics that I can share that really illustrate that point. California, no stranger to whiplash, of course, already something that is common in the background state of things, but which we do expect to increase imminently if it hasn't already. And indeed, we certainly have seen examples of that recently, and as recently as right now. That, this month we've arguably seen another iteration of dry to wet whiplash. Whether we see another increment from wet back to dry the same season will be another question to follow in the weeks to come. So a comment about how the wet areas in Sonoma got absorbed quickly. Would this be because the trees were extra thirsty? Usually it sits around longer, it seems. Well, I'm not an expert in the dynamics of vascular tissue in plants per se, which is essentially what that question would involve. But we do know that that's true of the soil, sort of as a passive sponge to a certain extent, where often, the drier the soil is, the more pore space that there is in the soil column and the more potential there is to absorb water. It doesn't always work like that in practice, but it can at least. If trees are water stressed and you give them water, then they will uptake more water more rapidly. So the active live tissues will do that. The question is, in some cases, whether some of these trees, deciduous trees, may have already been going some partially dormant for the season if they didn't have green leaves left on them for photosynthesis. Some trees still had leaves on them, and of course then we have conifers, the evergreens. So I don't fully know how much the trees would have played into that, although trees are really important for things like that, so I wouldn't be too surprised if there was a piece here, although it's complicated again by the fact that the deciduous ones were entering a different level of activity by the time this rain occurred. But I think the stronger argument, the clearer one, is that the soil itself had a lot of room to absorb that water, and that the rivers and reservoirs had sufficiently little water in them. They too, even when the soil got saturated, then had room to rise without rising to catastrophic levels. Yeah, it does look like the southern Bay Area will mostly miss out on the most intense effects of both of these storms. Most people at least got a decent soaking with the last one, or will with this one, but nothing all that remarkable in the southern parts of the Bay Area. That is the nature of the somewhat fickle atmospheric river variations. Often they occur in a fairly narrow range. There's a question from Kino Weatherman. We know a warmer planet holds more moisture in the atmosphere. Why are so many land masses abnormally dry or worse? Is it just raining in the ocean areas? This confuses me. This is actually a pretty relevant question to the question of increasing hydroclimate whiplash. The general answer is that, well, when it rains, it pours anywhere in a warming planet. So you see increased in precipitation intensity, but in many cases, decreased frequency of precipitation. So it's dry more often. And dry more intensely when it is dry. You see these huge increases in downpours locally, and what comes up must go down, but not necessarily in the same place. So there is, in fact, a more uniform increase in precipitation over most ocean regions than there is over land, and in many cases, the increase in precipitation extremes can be greater sometimes over the tropical oceans, for example, than almost anywhere else on Earth. However, the other reasons why land is becoming drier is because the land itself can exert a further drying effect. So as the evaporative demand of the atmosphere, I've talked about this before, this is the vapor pressure deficit, the expanding atmospheric sponge when it is dry, as that increases, the atmosphere literally demands more water from the landscape. So all else equal, you get the same amount of rain as you used to, but it's hotter and the atmospheric demand is higher. If you're not getting more rain than you used to, then you're going to have less water available than you used to because the atmosphere is pulling more of it back out of the land surface, back out of plants, back out of bodies of water, even if you have the same amount of rain on average as you used to. And compounding that, over land, it's warming faster than over the oceans. And so that atmospheric sponge is getting thirstier faster over land, which is then, in some cases during droughts, leading to faster warming. That's known as a positive or self-reinforcing or vicious cycle feedback, where the initial warming over land begets more drying preferentially over land, begets more warming, begets even more drying over land. That's sort of the toy model, the simplified version of it. The other, perhaps more interesting answer is that even if you account for that, it's still getting drier over many subtropical semi-arid land regions like California and the Southwest than we thought it was going to at this level of warming. And it can't be fully explained just by the expanding atmospheric sponge effect. So there is something else going on. We don't know exactly what it is yet. Relative humidity has actually decreased somewhat over land more than it was supposed to at this point. It wasn't supposed to decrease very much at all. But it has. Now, this is that question that I keep relating to. If you've been following these sessions over the months, I talk about this idea that El Nino has changed differently than we thought it would. And we've seen a trend toward a more La Nina-like average condition in the Pacific, contrary to many climate model predictions that the opposite might occur, a trend toward a more El Nino-like state. And the jury remains out as to whether we've just gotten randomly unlucky and this trend towards increasing La Nina-like state in the Pacific, contrary to what climate models suggest, will shortly reverse itself because it was unlikely to begin with and is essentially only being maintained by chance. That remains possible, but has become somewhat less likely the longer this goes on. Or whether there's something wrong with these predictions for the first half of the 21st century, and we should have expected a trend toward initially a more La Nina-like state, which is, of course, what we've actually observed. And there's some indication that the second hypothesis is probably closer to being true, in which case this does have implications for hydroclimate whiplash regionally, for trends in precipitation, for trends in wildfire severity and drought in particular, which might have been underestimated, at least in the near term, in places like California, but also in other drought and wildfire-prone regions globally. The interesting piece is that even those process-based models that say, hey, you really should have expected this trend toward a La Nina-like state, which is true when we use state-of-the-art, very high-resolution atmospheric models coupled with very high-resolution ocean models, which themselves can resolve what are known as mesoscale ocean eddies, so essentially these gyres on relatively small scales within the ocean themselves. Interestingly, those models tend to say, yeah, with warming, you should initially, for the first few decades of rapid warming, expect a trend toward increasingly La Nina-like conditions in the Pacific, as we've seen. And then, somewhere around the middle century, after about 30 to 50 years of that, suddenly things reverse, and you actually get a rapid shift, not just away from a La Nina-like state, but rapidly toward a more El Nino-like state on average. If that's true, then we're in for a pretty wild ride in the coming decades, because this La Nina-like trend perhaps was caused by human-caused global warming. We just got it somewhat wrong initially, but that eventually it's going to relatively quickly reverse itself and do what we thought it was going to do all along. Does this affect the fact that it's getting warmer? No, it's getting warmer rapidly either way. Does it affect the expectation that we'll see increasing precipitation whiplash in almost all land regions globally? No, that's likely to be true either way as well. So we can still infer a lot of the impacts either way. But does it affect the relative rate of increase of drought risk versus flood risk in a place like California? Yes, it probably does. Does it mean we should be preparing for rather different levels of drought and wildfire risk versus flood risk in, say, the next 20 years versus the 20 years after that? That's a more difficult question to answer, and is really at the crux of some difficult conversations I've been having in recent months, to be quite honest with you. So we don't know, and this could get interesting, so stay tuned. And also read the discussion in our review coming out in early 2025 for a little more philosophical expounding on that topic. Question, has it snowed less in the eastern U.S. because of global warming? Yes, that one's pretty easy. There's been a large decrease in light to moderate snow events and no decrease in most cases in the most extreme snow events, which is very interesting. This is exactly what you would expect in a climate that was occasionally supportive of huge snowstorms, but generally was right on the cusp of being too warm for it. This is because there's a competing effect, I've mentioned this before as well, between warming temperatures has two different effects. On the one hand, warmer temperatures, you might expect, you're on the correct side of the freezing line, so your temperatures are either below or above freezing, and you're more often above freezing as you get warmer. That stands to reason, and of course it's true. That means that thermally, temperature-wise, you're less often experiencing conditions that are cold enough for snow. But when it is cold enough for snow, even if it's just marginally cold enough for snow, now we've got 7% per degree centigrade of warming more moisture in the atmosphere. So you actually then have this competing effect where temperatures are less and less favorable for snow on average, but if it's really cold to begin with, say your temperature 50 years ago would have been 25 degrees during a storm and now it's 30 degrees. Well, that's still on the correct side of the freezing line, and now you have 5 degrees Fahrenheit worth of warming of increased moisture, so you can get more extreme snowfall rates. So what we see in the eastern U.S. is a decrease in average snowfall and in small snow events, but we get just as big extreme snow events as we've ever gotten, and in some cases we've even seen slightly larger extreme snow events on the rare occasions when that increasing moisture outweighs the direct thermal effect of it being warmer and therefore less icy than it used to be at the surface. So this is a dynamic we'll continue to see play out, and there's even some indication on the eastern seaboard that the very most extreme snow events will continue to be just extreme as they always have been, even with very high levels of warming, but those will be almost the only snow events that occur. There will no longer be picturesque dustings. It'll either just be rain or you get 3 feet of snow all at once. So that's going to pose its own climate adaptation and management problems. As I've raised before, I was in New York earlier this year and talking with some folks in upstate New York about how, in upstate New York, they're used to big snowfalls, and they're going to get one this week, by the way, a huge lake effect snowfalls all throughout the Great Lakes region for Thanksgiving, which will be a bit of a travel nightmare for anyone going up there. But this notion that places like New York City or Boston even, but especially places like Washington, D.C., which are a little farther south and warmer on average, but still occasionally get large snowstorms. Think about Snowmageddon, all of these dramatic social media era terms for specific snowstorms there, where D.C. gets 18 inches, 24 inches, 30 inches of snow in 2 days, and it completely shuts down the city and air travel and highways and all of that. And yet, there have been recent years where it hasn't snowed at all in some of these cities, but they're clearly still capable of getting these 2 or 3 foot snowfalls all at once. So what do you do if you're Washington D.C. Fleet manager for the snow plows? You literally won't use them at all, more often than not in a typical year in a warming climate. But every once in a while, you're going to need all of them all at once, and they still won't be enough. So how do you manage that? Again, another example of the mean or average condition change not being very representative of the change in the most extreme events, and that's a fairly visceral, visible example of that. So there's a question from Lily about the way we're talking about floods changing, 100-year event and 20-year event. I actually covered this at some length in the beginning of the conversation with respect to rain events. I wasn't talking about floods specifically, but the exact same conversation would apply. So if you missed that, that'll be available for viewing afterward via the recording. But in general, you're right, that what was once the 100-year event, if it becomes more likely or extreme events are becoming more intense, what was once the 100-year event might now be the 80-year event or even the 50-year event, or perhaps even the 20-year event, because it's becoming progressively less rare to see an event of an equivalent magnitude. That would be the logic there. So you've got the general sense of things right. For the details, refer back to the beginning. All right, folks. Well, I'm going to keep it right to the hour for once. Thanks for joining, and I have a good Thanksgiving week. This will probably be the last session I do this week because there's no particularly extreme conditions on the horizon for California, but I'll try and be back at it the week after, when it will likely be warm and dry if you're outside of the Central Valley, or clammy and foggy, potentially, if you're under the inversion layer. So with that, thanks all for joining. The link to that documentary I mentioned is the second or third comment in the chat section, so feel free to check that out. And I'll talk to you next time.